Hi everyone. So do we get continuity at x equals 1 or not? All right, let's take a look at this second rule on the second subdomain. The second subdomain is the closed interval from 1 to 2. The left endpoint of the subdomain is at x equals 1. The right endpoint is at x equals 2. Bear in mind, these don't always match. Here they do. Okay, let's see if we can get continuity here. Let's plug in these two endpoint values into this rule, x plus 1. So y equals 1 plus 1. That's going to be not 1, but 2, which means that the corresponding point is going to be at 1 comma 2. That's going to be the left endpoint for the second piece. Now 1 comma 2 is a different point from 1 comma 1. There's no way that we're going to have continuity. There's going to be a jump here. Because of the bar there, we have a weak inequality. X equals 1 is included as part of this subdomain. The point 1 comma 2 is included as part of the second piece of the graph. Now, what about the right endpoint of the subdomain, x equals 2? Let's find the right endpoint for the second piece of the graph. Plug in 2 into x. Y equals 2 plus 1, or 3, which means that the corresponding point on this piece will be 2 comma 3. But is it included or excluded? Because of the bar there, it's a weak inequality. X equals 2 is part of the subdomain. Included. The point 2, 3 is included. So both endpoints are included on the second piece of the graph. Well, now what? Well, we've now answered the questions. What pieces of these graphs do we want? What piece of the red graph, what piece of the blue graph do we want? And we can now graph the overall graph, which looks like this. And by the way, it's great that you're seeing this video because this grid is actually not a part of my notes. I describe it in my notes, but the grid helps a lot. It's a good thing you're watching this video. Here's the graph of the function. So the first piece is part of a parabola with vertex at the origin, although you could point plot also. The left endpoint is at -2, comma 4 up here. That's included as part of that first piece, the left endpoint. The right endpoint at 1 comma 1, however, is excluded. Because the left endpoint is included, I'm putting a nice solid dot at -2 comma 4. Because the right endpoint at 1 comma 1 is excluded, I'm putting an open hollow circle at the right endpoint. By the way, we call this an open endpoint, not a hole. It's not a hole because there are no points immediately to the right of it. It's an open endpoint at the right end of this first piece. That's the piece of the red parabola that we want. Now, what about this piece of line, this line segment that we see here? Well, I want a piece of the slanted line that's going from 1 comma 2 to 2 comma 3, and I want to include both endpoints. Well, we're going from 1 comma 2 to 2 comma 3 along the slanted line segment, and we're including both endpoints. Solid filled in dots at the endpoints. That barbell. Again, notice that 1, 2, and 1, 1 are different points. There's a jump here. In fact, we say in calculus that there's a jump discontinuity at x equals 1. In order to get from this graph to the other, you have to jump up onto this piece. Also in calculus, we would say that the function, as x approaches 1 from the left, approaches 1 in function value or y coordinate. That's the y coordinate of that endpoint. And from the right, the limit as x approaches 1 from the right is 2. The function values approach 2. So again, And I talk more about limits later on in the notes, but as x approaches 1, the left-hand limit, as you come in from the left-hand limit is 1. The y-coordinates approach 1 from the left. The right-hand limit is 2, because the y-coordinates or function values approach 2 from the right. Now again, the reason why we were able to get the point 1, 1 as the right endpoint for this piece is that, hey, 0.9, comma 0.9 squared, that's a point on this graph. 0.99, comma 0.99 squared, that's a point in this graph. This piece of the graph, if you walk along this piece of the graph, you're approaching 1, comma 1, even though you're not allowed to reach it. In fact, this idea of a limit, it doesn't care whether the function values actually exist or not. It doesn't matter if you have open endpoints here or not. The right-hand limit would still be 2, whether it was an open endpoint or closed endpoint. By the way, if I had made this a solid filled-in circle, a solid filled-in dot, if I had thought that the right endpoint were included on the first piece, how would I know that I was wrong? This graph would just barely fail what test? The vertical line test, right there at x equals 1, which means that it cannot be the case that both these endpoints are included. It's possible that both might be excluded. A function allows for this, an open endpoint at 1, comma 2, but you cannot have a point at 1, 1, and 1, 2, both included on the graph, if y is a function of x. This, however, is okay. So remember, your final graph has to pass the VLT, the vertical line test. Don't just turn this in as a final answer. This massively fails the VLT, the red and blue graph together. However, notice here, this graph does pass the VLT. And notice, this is the entire graph. There are no arrows going off anywhere off towards infinity or whatever. This is the entire graph. I'll erase these. There's no arrow stuff going on as this stands. This is the entire graph with finite arc length. The entire graph. There's nothing beyond what you see here. What you see is what you get. That's the entire graph. We'll talk more about piecewise functions later on.